Welcome to another video of terrain materials. In this video, we'll be discussing about phase diagrams. So, what are phase diagrams? Basically, it is used in physical chemistry and engineering, especially in material sciences. So, it's a kind of a chart that is used to show some conditions at which thermodynamically distinct phases occur, and also they coexist at equilibrium. So let's discuss some basic concepts first. So you know that in the components of system there are some independent chemical species which comprise the system. These could be elements, these could be compounds, these could be ionic. For example, is given the silver copper system, the ice water system, the alumina and the bromate system. So what are basically phases? Phases are physically homogeneous and distinct portion of the material system. For example, it is a gas, a crystal, or it is amorphous in nature. Basically, we have three phases in which we have gases, liquids, and solids, and you know about it in detail. So next we have a solute, which is present in the minor quantity, or you can say that is the lesser quantity. And we have the solvent, which is either liquid or solid. It is also present in the greater quantity or the major component of the phase, and both of them combine, the solid and the solvent combine to form a solution. Then we have a system. So what is a system? The system refers to a body of a material or an object. In this case, we refer to an alloy system or a series of elements. Then we have solubility limits. So what is solubility limit? It is basically the maximum concentrations of solute atoms that may be dissolved in the solvent in order to form a solid solution or a solution. That limit, that extent is called solubility limit. Moving forward, this is a phase diagram in which we can see that we have two components. One is temperature and the other one is composition. We can also make the diagram between temperature and pressure and composition. So if we are discussing two components, the third would be constant. So this diagram would be on a constant pressure. So what is happening in this, that this is the sugar water uh, component, in which here we have water, that is the solvent, which is 100%. We have more sugar over here, and now we are increasing the quantity of sugar, uh, and you can see that here is 100% of solute, that is sugar, and there is no more solvent left to dissolve that. So this is the solubility limit. You can see on the left we have temperatures 0 to 100 degrees, and this is the liquid syrup of the sugar and water system, and this is the solubility limit. So we can find out that from this diagram that, for example, at 40 degrees Celsius, 60% or more than around 68% sugar can be dissolved in water, and after that we increase the temperature. You can see that the solubility limit of sugar is increasing. However, the maximum 80% of the sugar can be dissolved. As you can see that after 100, the boiling point of the water will be achieved, and there won't be any more water to uh, dissolve the sugar. So here the solubility limit of the sugar dissolvable water will end over here. So this is like this is what phase diagram looks like. Then we have a microstructure. The properties of an alloy does not only depend on the proportions of the phases, but they also depend on how they're arranged structurally and on a microscopic level. So you can see over here that there are two microstructures of the aluminum copper alloy, and it's specified by the number of phases, the proportions, and the arrangement in space. So you can see that the beta phase is the lighter phase, which is the uh, solute, and the darker phase, alpha is the darker phase, which is the solvent. You can see over here that this area is of the solvent, and the other area, the lighter area, is of the solute. So then we have metallography. In order to find the microstructure, we do metallography of specimen. First of all, we do have to prepare some specimen for you know visualizing the microstructure on a microscope. So first of all, we section our material, we cut the material at the desired size we want, and then we mount it with organic physics in order so we can easily hold our sample, and then we grind and polish the material in order to remove the scratches. Then we etch it with a chemical, and usually in acids dissolved in water, or I can say that diluted in water. So that reveals the internal structure that we can visualize in the microscope. Otherwise, if we directly put the polished surface, we will be just seeing the reflections of the structure of the surface, not the structure. So this is how micrography is done. We must have done it in the lab. So this is the sectional part. We cut this, cut our material, that is the material that size we want, the grinder basically, and then we mount it and grand polish it. The grinding and polishing machine. We use different grid size papers and progressive manner, and then we polish it on a polished pad, and this is how the structure looks like when we visualize it in the microscope. So this structure is of a low carbon steel. Next we have phase equilibrium. So in this we have fixed free energy, which is delta G delta H between enthalpy minus temperature, the product of thermal entropy. So, you know the thing, entropy is the amount of disorder, and in a system which is at equilibrium, if we have a constant temperature, pressure, and a composition, the system is stable. That means that the system won't be changing with time. So that means that the system would be in equilibrium. Equilibrium is the state that is achieved uh, uh, given within a sufficient time. And the term phase equilibrium or phase equilibrium is often used in the context of the discussion, which refers to equilibrium, and it only applies to a system in which there is no more than one phase present. There is only one phase present, not the other phases which coexist. So that is called phase equilibrium. But in reality, we also have metastable phases. Uh, so this the state without equilibrium is called a metastable state or an unstable state. But you can see over here that this is the free energy and this is the metastable state and this is the equilibrium state. So what is basically a metastable state? In this, there will be more than one phases which would be coexistent. That means they will be solid and liquid existing together. They will be liquid or gas, or they will be uh, gas, and solid. So let's read this. But the time to achieve equilibrium may be very long. Again, while pulling the if we want to achieve equilibrium, it will take a lot of our time, and the kinetics will also be slow. So that a stage along the path to the equilibrium may appear to be stable. This is called metastasis. If we are doing very quickly, so we have a metastasis. That is basically a state which is trapped in a local minimum of free energy. That is not the global one. Okay? So we'll be discussing this more in the later slides. Now we have a one component, or we can say unitary phase diagram, in which we only have water over here. So we are not taking the composition. We are taking two components, one of pressure and one of temperature. The externally controllable parameter that will affect phase structure is pressure, temperature, and composition, as I discussed in the previous slides. But here we are only taking pressure and temperature, because we only have water. We don't have another solute that we could dissolving in this. Here you can see that there are three phases. One is solid, one is liquid phase, which is water, and third one is steam, and that is vapor phase. So at 0 degree, what we have is we have the triple point over here at 0 degree, and at 0.01 atmospheric pressure. You can see that all the three phases are coexisting, which is the solid phase and the liquid phase and the vapor. All of them coexist at this temperature and pressure. So this, especially this point, would be known as triple point. Okay. Generally we discuss at 1 atm, which is at 0 degree. We have the freezing point and the melting point of ice. So we have ice below 0, and we have liquid water after the 0 degree. So here triple point is important, at which all three states, or you can say all the phases coexist. Then we have a binary phase diagram, or binary isomorphous system. You can see the same structure system. There are no different structures. There is only one structure. There are two components. For example, if you look at this example, that this we have all the composition of A over here, which is our solvent, and B is being dissolved in solvent. So the percentage diffusion of the B solute. So what we can see that this is the liquid region, and this is the liquidus plant below which the liquid will be starting to convert into solid particles, because as we are cooling down, the liquid would eventually convert into solid after its freezing point. But here we are discussing a solution. As we can say a solid solution, or any solution. So in a solution, the solution is not a pure substance. So here we can see that there is a solidus and a liquidus line, and in between that line there is some gap. If the substance would be a pure substance, there won't be a gap, but there is a gap between the liquidus and the solidus line, because this is not a pure substance. This is a solution. Okay, but if you look at this point A, there's only one point, because there is only A present. A can be whatever substance, but there is only one substance that is A, which is a pure substance. If there is only a single point, that means there is only one point, which is the solidus and the liquidus point. And at B, which is 1% of B, and there is no A, which means that B is only present, and B alone is the pure material or the pure substance. So this has only also has one freezing and melting point. That is this. But when we move along the composition of B, when we start to add V in A, which is our solvent. So you can see that this gas is being observed. That means there is no proper, that there is no one line which is the liquidus and the solidus. Okay. So on the left, we can see that we have taken certain compositions. We have taken around 6 compositions, in which starting with 100% of A and ending up with 1% of B with 0% of A, and we have started to increase uh, the percentage of solvent E over here, and we have cooling it down. So this is a time temperature cooling, which is called the Ptt diagram. Okay, so these are basically experimental values. They're experimental cooling curves, and you can see over here that this curve is being developed by these time temperature cooling figures. So we have obtained this leaf-like figure above that, which is the liquid part, and below that is the solidus part. So this line is liquidus line, below which the freezing would be starting if we turned on the temperature, and here you can see that the liquid would start to be converting in the solid phase. So this would have both the liquid phase and the solid phase, which is alpha. It's called alpha. So that is mentioned over here. And when all of the liquid would be converted into alpha, which is solid, so this is the solid line, below which there would be only the solid solution, not anything else. That is called alpha over here. Okay, so basically this region in which both the states coexist, that is liquid and the solid state. So this state is the metastable state. Above that is the equilibrium state, and below that there is also the equilibrium state. Okay, so this is what I was discussing in the previous slide. So moving on, here we have phase diagrams, which indicates phase is a function of time, temperature, and pressure. For this course, binary systems, we are going to be discussing binary system only, which has two components. One is the independent variable, that is temperature, and uh, the composition is is also the independent variable. Here, pressure is usually always 1 atm, so we are not considering pressure over here. So in the phase diagram, on the y-axis, we are having the temperature, which is 1600, which is up to 1600 degrees in this case, and we are discussing a copper nickel system, in which there is percentage of nickel being increased. So this is somewhat similar as we discussed in the previous slide. So this is the whole of the liquid region, and so this is the liquidus line, the solidus line. This phase in between the L plus alpha, that is liquid plus alpha, the solid phase, is the metastable state, and then we will be having the FCC copper nickel system, because both the phases are FCC with the copper water nickel or copper, both are FCC. So we will be getting an FCC solid solution. Moving on, here we have an isomorphous binary phase diagram. Isomorphous means the same structure, we are getting only FCC over here. So this is the system which is binary system, that is two components, copper and nickel. Again, we discussed this earlier. Isomorphous, that is completely soluble of one component and another, that is alpha phase. Field extends from 0 to 3% weight nickel. That is in this part. The copper would be completely dissolvable. Sorry, the nickel would completely dissolvable in the copper phase. So let's discuss let's interpret the phase diagrams over here. Okay? So how can we determine the phases? So rule number one is if we know the temperature and composition, then we know which phases are present. So if we have if we want to find a specific temperature and composition, we can find out at which phase it is present at. For example, we are considering point A, which has 1100 degrees centigrade temperature and it's around 60% of it. From that, but we are taking it as an approximate. Okay, so in this case, phase present is a solid phase, which is an FCC phase. But now, if we are discussing this 1250 degree centigrade, which has 35% of nickel. Uh, Again, these are approximate values. This is not given property. And at 13, at 1250 degree centigrade, at 35% nickel, which is around here. Now you can see that the phase is present is liquid plus alpha. It's not mentioned correctly over here, but it would be around here. I should just draw it for you guys. At 1100 and at 60% nickel would be this phase, alpha phase, solidus phase. And for this, we can look at the color. For 1250 degree centigrade, 35% weight nickel. So this is the 1250 and around the 35% weight nickel. You can see that this is the metastable state in which both liquid and the alpha phase are present. And we have been talking about at 1400 degrees centigrade and at around 20% nickel will be in the liquid phase. Okay. So next we have determination of phase compositions. If we know the temperature and composition, then we can determine the composition of each phase. Yes, what composition of each phase we have. If we consider that the composition is 35% nickel around here, and we have just shortened the diagram because here this is the zoomed version for this. If we have 30% or 35% of nickel and at 1320 degrees Celsius, so we'll be getting only the liquid phase. We will only have 35% of nickel. However, if we discuss at 1120, this is for 1190, this is 1190, okay? And at the same composition, which is 35%, we'll be getting 35% nickel, but here we'll be having the solid phase, okay? But if we discuss at 1250 degrees centigrade and at 35% of nickel, we'll be having both phases, that is the alpha phase and the liquid, both solid phase and the liquid phase. So what are the compositions of these phases? So we have to find it out. So what we'll be doing is we'll be drawing a horizontal line from this point, point B, in which our composition is 35% and the temperature is 1250. We'll be drawing a tie line, which is a horizontal line perpendicular to this line, and which intersects the solidus and the liquidus line. So by the tie line and from the liberal rule, we'll be calculating the percentages of the phase, the liquid phase and the alpha phase present. Okay. So we can say that both alpha and the liquid are present. So composition of Cl equals to C liquid. The liquid is state 32% nickel, drawing perpendicular from the tie line, and the solidus line we are drawing a perpendicular as well, which would be 43% of uh, nickel. Now, if we want to determine the weight fractions of that, okay, so how much weight fractions have of nickel and of the liquid phase and the solidus side itself. So here we will be applying lever rule. We have the skyline, which is divided into two, which is so this one is R, the green one, and the blue one is you named it S. Okay. At the A, only liquid phase are present. B, only solid phase is present, and B, they are both present. So at D, there would be only the weight fraction of liquid would be 1, which is the maximum, or we can say 100%, and the weight fraction of uh, solid at point D would be 1, which would be 100% again, and of that of liquid would be 0, as we see from the diagram. However, if we are talking about point B, we have to calculate the phase of the liquid and the weight fraction of the solid phase as well. So what we'll be doing, we'll be dividing the tie line uh, from the perpendicular line of the compositions. This part is R, and this part is S. So for the liquid weight fraction, what we'll be doing is we'll be dividing this S, which touches the solidus line, upon the total length of R and S, which is around 8. We have 32 over here, and we have 43 over here. R plus 43 is around 11. So if we are dividing this, we're getting 0.7. If you don't know the exact length, if you want to find the exact length, what you can do is you can just take S as 43 minus 35, and you just take the whole distance over here, which is 43 minus 32. So both the methods are correct, but whichever is easier to use, you can find it out. And for weight fraction of alpha, which is the solid part, you could just subtract it from 1, because there are only two phases, and you can get the other one, which is 0.27, or otherwise you can follow the same rule. Okay, so basically this is called lever rule. You can also study this from the Callister book, William P. Callister. The tie line connects the phases in equilibrium with each other, also sometimes called an isothermal line or an isotherm. So these are also called isotherm. Okay, and again, this is the formula for the lever rule, which calculates you, or which gives you the weight fractions of the liquid and the solid. Then we have an example of a copper nickel alloy. This is the phase diagram of copper nickel alloy. Again, it's the shortened version. You cannot see all the percentages of nickel, only from 20% to around 55 or 60%. So now we'll also be discussing what uh, microstructural changes have been we can observe. Okay, so consider the microstructural changes that accompany the cooling of a 35% weight percent nickel core. Okay, so this is again the copper nickel system, and we have shortened the diagram. So now we'll be discussing the microstructural changes uh, from the liquid phase to the towards the solid phase. Okay, so here we can see in the liquid region we only have liquid, which is homogeneous phase, and you can see it in the dark green. Then if we while cooling, if we reach at point B, so we can see that there are some nuclei which are grown uh, within the liquid as we increase the temperature, as we lower the temperature. So this is and this we have around 35% nickel, this equation of equivalent alpha. So while this is in between the metastable state now at points, we see that these nuclei are being grown and we see the size of the nuclei are growing, which could be converted into grains. Now at point D in the solidus line, that grains are now very much visible, and there is the liquid part is very less than this. And after D, at point E, which is completely the solid, there is no more liquid present, and we can see that all the liquid is converted into the solid form and visible green boundaries. Okay, so this is microstructural changes when we are considering a binary system. This is another diagram which shows the same thing, that at point A there was negative, at point B there was some solid nuclei being made on the liquidus line. After that, this is the metastable state at C. You can see that the alpha particles start being going, and point D, where the coastal greens, dark greens are being grown, and after the solidus line, you can see that if you reduce the temperature more, so all the liquid part is disappeared now, and have alpha green. So this is achieved in only in the equilibrium conditions, or you can say the equilibrium cooling, which is very slow and very difficult to achieve. So we need sufficient amount of time to achieve the equilibrium. Okay, and that is whereas this free energy is in its lowest possible. So we have this least free energy level, but this process is very slow. Now let's initiate between the equilibrium conditions and the non-equilibrium cooling conditions. So you can see that this is the same thing which we discussed while comparing with non-equilibrium cooling, in which we can say that what is non-equilibrium cooling. In this, we don't cool our substance with a fixed rate. For example, if we are cooling in this system, in the equilibrium cooling, we are cooling it with a fixed rate that is of 10 degrees per minute, or 15 degrees per minute, or 5 degrees per minute. Okay, but in non-equilibrium cooling, the rate is too high. It's around 50 degrees per minute, or 55 degrees per minute, or 60 degrees per minute, and the rate also be changing. So we'll be visualizing some pouring in this stuff. Okay, so let's start from here. The liquid phase, you can see that this is the same as the equilibrium cooling. While going down to the liquidus line, the solid particles have started nucleating. The embryos are starting developing. Then in the middle, the metal stable state, you see that the embryos are been growing. But now uh, uh, the inner part is not yet completely solidified, but the other part is being solidified now. So there is a thermal differential between both of them, and the heat is not diffusing out properly. So at D, you can see there is pouring being observed, because when the inner part is not completely solidified, and on top of that, there is a liquid layer being formed, which resists the heat diffusing out from the inner part. That is being formed. Just visualize the part E and part F. You will be seeing different structures in solid, in the final solid solution. Okay. cold versus equilibrium structure. So this is the equilibrium structure. You can see uh, from liquid and solid to liquid again, and result of a fast cooling rate, you observe a cold structure. So this is what once solid nuclei is formed, and then nuclei after nuclei are being formed on the same first nuclei, but they are not properly cooled. The heat is not using out properly in a specific rate because there is no time. We're not giving it much time in order that the heat is being extracted from the core itself. So this is called the core structure. Okay. Sometimes this core structure is useful. For example, if you are talking about the gears, the gear teeth on the surface are very hard because they need a higher strength. But in order to absorb the shocks higher while changing the gear, it needs to absorb some stresses, okay, so internal stresses or some applied load. So the inner structure is being poured, but that is made soft so that all the stresses coming out from the surface is being absorbed uh, inside that core. Okay. So we have some points of non-equilibrium cooling. Let's discuss. One is achieving physical equilibrium is not possible. If it's possible, we have to apply process parameters very carefully, and we have to observe it very sharp so that there is no more non-equilibrium present over there. With changes in temperature, there is a readjustment in composition again, and this is true as well. While we are changing temperature continuously, uh, uh, and the cooling rate is not, you know, defined very well. So there are also some readjustments in the composition. These readjustments are accompanied by diffusional process. As I discussed earlier, that there is no time for the temperature or for the heat in order to diffuse out from the inside. So diffusion is a time-dependent process. It takes time. Again, liquid have high diffusion rates, while solids have low diffusion rate. Since the diffusion rate of solids is very low, so we have to give a lot of time in order to get an equilibrium phase. So in equilibrium, the liquid phase is maintained while in solid non-equilibrium cooling takes place. Okay? And so in the liquid region, um, in this liquid region, the equilibrium is maintained while cooling down. In actual in practice, the equilibrium is not maintained and the cooling is not equilibrium. So greater proportion of liquid is present for these non-equilibrium conditions than equilibrium cooling. Okay? As I discussed, the slower the cooling rate, the smaller the differences between equilibrium and non-equilibrium structures. This the structure developed called force equation, as discussed in these slides. Moving forward, uh, then we have mechanical properties of a copper nickel system, which is effects of solid solution strengthening on tensile strength and ductility in terms of percentage elongation. You can see that once we increase the percentage of nickel in the copper system, the copper solvent, the strength of copper is increased up to this point up to 60%. But after that, this is the threshold. After that, the tensile strength is being reduced. So should not add much nickel beyond 60% if you want to achieve the higher strength. Okay, but by adding nickel, we are also compromising the ductility. So if you want to have a minimum of 40% ductility, you should only add about 20% nickel. But if you are further adding the nickel for strength, you should know that the ductility is being compromised. However, if you are adding more nickel, you can get a bit of good tensile strength and ductility as well. Okay, so this was the part 1 of phase diagrams. I will be discussing binary eutectic systems in the part 2 of this lecture. Okay, so thank you guys.